let's kick off the rest of our talks. We've got Matthew coming in to talk to us about something that's going to give you nightmares for the rest of the day. So,
Hi, everybody. Thanks for having me back after my first talk with the horrors of QR codes. The title is a little bit misleading. I couldn't quite fit a million ways to get hacked on the web into 15 minutes. So, unfortunately, it's going to be 3 ways. It's the best that I could do, and it's still it's a little bit of a tight squeeze. A little bit about me. I work in cybersecurity and have done for the majority of my career. And prior to that, I still did some cybersecurity, but less professionally, shall we say. Very fortunately got employed to do it as a job before I got arrested. So it's a nice outcome for me. It's another outcome, yeah. So if you fancy talking anything about cybersecurity after this, or anything in general, really, just please add me on LinkedIn. First up, this is going to be something of a whistle-stop tour of some of the more common ways in which we exploit systems. And by exploit, I mean get them to do things that we didn't intend as developers for people to be able to do with them. Usually, if you're a bad actor, this means trying to compromise somebody's system, exfiltrate data, escalate your level of privilege within inside an application to do bad things. Most people are kind of familiar with ransomware and all the terrible things that come out of incidents like Optus and stuff like that. Here with buffer overflows, we're going all the way back to sort of the beginnings of cybersecurity. These were some of the very first types of exploits that were publicly known. Way back to like 1977, I think was like the first of these that was ever academically published. So what actually is a buffer overflow? It's a little bit of a computer science lesson. And for anybody that's done computer science, I realize that's not an accurate representation of the stack, but it's close enough for our purposes. When an application runs, you need memory for the application to run in, right? You need to be able to store the code that is currently running. You need to be able to store variables that your application is using, storing data that's being input by a user or by other systems. And you need this thing called a return address. So whenever a function gets to the end of its operation, in a piece of software, it needs to know where to go back to. It's usually been called by another function, right? It's being run by something else and needs to know to return to that function to carry on the rest of your program. And the way that these things are set out in memory used to look a little bit like this. You had a program function, some variable space, and a return address, and then unallocated is kind of the rest of your computer's memory. So putting something into a variable looks a little bit like that. You've inserted some text into whatever variable you want. So what bad things can we do with this? Well, in a lot of older programming languages, there weren't really many protections within its core functions, right? So the bits of the programming language that you use to get variables and set variables and perform various actions, they trusted you as the programmer to know what you were doing with them. And even if you did know what you were doing with them, they're still incredibly dangerous. What you can do is this. You can exceed the length of the variable. So if we had a text field that was set to like 5 characters, there'd be nothing to stop me putting as much data in there as I wanted to. What that does in memory is it spills out or overflows into the rest of the stack. What's notable here is that it overwrites the return address and then goes beyond that into unallocated memory. Now, if you just put some garbage in there, the most likely thing that you'll get to happen is an error called a segmentation fault. This is the computer realizing that you've gone out of the bounds of the memory, you've overwritten your return pointer, and now it just crashes, kills the program. What you can do, though, is you can exploit that ability to overwrite the rest of the address space. So if we run, or if we interact with the program in a way that fills the variable space, we can now insert other things into the return address, right? We can get the return pointer to look at a different part of memory. A little bit like that. The useful thing about this is that you can insert your own payload into the end, right? You can get that pointer to point to your code instead of the application's code. And you can insert all of this in one go, into what would be a normal variable. Has anybody got any ideas as to what you could do with something like that? I'm going to try and do a live demonstration of this. So one of the most useful things that you can do with this, or one of the most dangerous things you can do with this, is you can achieve a root level of access to somebody else's system. So here, I won't go into too much detail because I don't really have enough time, but there's a section called padding. That is there to fill up the variable space in the stack, right? So this pushes us to the end of the stack and then gives us the ability to write beyond that and into the return pointer and the rest of the system's memory. Down here, in shellcode, this is executable by the computer. What this particular shellcode does is give us a command prompt. The command prompt that we get is at whatever privilege level the application is running at on the victim's machine. In this instance, hopefully, if I run this, so we've connected to a remote machine. I'm running 2 virtual machines. You just have to trust me for the moment. It's found the start of the buffer, and it's now ready to run my exploit against it. So if I do that, you see that the remote application has returned the padding that I've sent it, because that's all this program is basically designed to do. It just repeats back to you what it's been sent. It's kind of an imitation of a server. And now, if I do this, I now have root access to that machine. If I do ls, I can now navigate to that machine's web directory and interact with it and do whatever I want with it, right? At this point, what you would usually do is install extra software. This gives you the initial access into the system. What you want to do is persist access, right? So from here, you download things like rootkits that bury themselves away into the core of the server that you've compromised and give you a persistent level of access that doesn't rely on this exploit. So these were backup slides just in case I... So as I said, this happens because of unsafe functions within programming languages. This was written in C. And these are some of the unsafe functions that exist within C that we never, ever, ever use anymore. These have all been replaced by safer functions, but not entirely safe. As I said, this is really old stuff, right? These are exploits that go back a very, very long way. So is it still an issue? Well, funnily enough, yes, it is. Despite the fact that this should not be happening anymore, a new CVE was published just a few days ago, in fact. This compromises every Linux-based system on the planet, which is not too bad if you've got a system you can update, terrible if you've got an IoT device that you can't run any updates against. I'm going to try and speed through this one in the time that I've got left. SQL injection, this is one of my favorites. You can't talk about SQL injection without including XKCD. Little Bobby tables, yeah. This is excellent. I love this so much. Basically, I share this with anybody every time I talk about SQL. So what is SQL injection? Well, when we interact with a web application, it's usually talking to an SQL database somewhere in the back end, right? And we're running queries against it. What if we run a query that includes SQL? Well, in this case, we escape the actual query that's being run. And now we're trying to retrieve username and passwords from the users table. You can do pretty much anything you want at that point within the database, right? You can exfiltrate data, you can insert new data to gain access to admin panels and things like that. How does it work? Well, the way that it works is that we're modifying the query that happens on the server. SQL was often written in an unsafe manner, where the actual query that gets run in software is built from the string that gets input by the user, and we can't trust users, basically. So if a user is allowed to interact with what the software is doing in a very close way, you get bad results. These are two good examples. So the first one's interesting because it's just a logic error, right? You're saying or 1 equals 1, which always returns true. That's particularly useful for breaking into like password protected pages and things like that. And that's basically what the query ends up looking like once you've interacted with it. You end the query prematurely, insert your own query, and then at the end, you notice the 2 dashes, which is the comment symbol for SQL. You're telling it to ignore the rest of the query. So it doesn't matter what else the program was told to do after your query. It just finishes there. Now, I'll skip the live demo for this one and show you the screenshot. Well, I'll ignore the screenshot. Actually, I didn't finish it. Oh, no, I did. I was put it in the wrong place. Forgive me. So in this instance, yeah, what we're doing is we're joining the users table to a product table. So because the code itself is only ever designed to return product information, we have to try to convince it to display data from a different table. So you do things like a union and insert your new data into the SQL data that it would normally return. This is like a solved issue, right? We've known about this for 30 years, more maybe, and everybody knows to use safe functions where this never, ever, ever happens. Except when MoveIt, one of the most popular enterprise pieces of software in the world, was victim to an SQL injection exploit and divulged British Airways data to the dark web. So these things still happen. No matter how long they've been about, they still end up being problems today. Modern attacks actually don't rely on any of these most of the time. Modern attacks rely on your user identity more than anything else. 88% of breaches for the past year were all down to user identity, not for an exploit of an intricate nature or SQL or anything like that. 30 billion identity attacks every month. This is the number one way in which you are going to get compromised. And it's the number one thing that you have to take care of. And I'll end there. Thank you very much.
Looking for sensitive questions. Look, I know that we were that.
An identity is basically when somebody steals your username and password, right? And bypasses a control like multi-factor authentication. These things are designed. You can't trust passwords anymore. The password is dead, basically. And you have to rely on secondary controls like MFA.
The question I have, which might be spam as well, is HTML programming language. So I'm going to see if that. if you wrote this in the last 10 minutes, but I don't know if people are across the curl thing. But that's a buffer overflow.
Yeah.
That happened. Like they just brought it out, the announcement at 5:30 tonight.
Yeah.
What the actual issue was, and
I heard about it earlier today. Yeah.
Yeah. Well, I didn't think they said what it was. So if
Yeah.
anybody ever uses curl,
Installed on every single Linux operating system everywhere. Yeah. So yeah, the buffer overflows are still happening every single day,
today,
including today. Yeah.
anyone else having any useful questions? Don't bother to know.
That person that was charged with funding prosecutors were looking at the HTML code of a government website.
In the early days of cybersecurity, yes, people were prosecuted for all sorts of stupid things. This was recent. All right. Okay.
No further questions?
Excellent. Yeah.
Yeah. Check the curls.
Thank you very much, everybody.